welcome to this problem walkthrough. Today, we'll be tackling an interesting problem titled Remove Max Number of Edges to Keep Graph Fully Traversable. We'll explore the problem statement, understand its constraints, and dive into various approaches to solve it efficiently. Let's get started. The problem revolves around Alice and Bob working together on a graph that consists of n nodes, numbered from 1 to n. The graph has edges, each represented as a triplet, type U, V. Here, type specifies who can use the edge. Alice-only edges are denoted by 1, Bob-only edges by 2, and shared edges, usable by both Alice and Bob, are denoted by 3. The nodes U and V are the two endpoints connected by the edge. The objective is to ensure that both Alice and Bob can fully traverse the graph, meaning they can reach all nodes starting from any node. While doing so, we aim to remove the maximum number of edges. If it's not possible to make the graph fully traversable for one or both users, the output should be -1. The input consists of the number of nodes n and a 2D array edges that describes the edges, and the output is the maximum number of edges that can be removed while maintaining full traversability. The output is a single integer representing the maximum number of edges that can be removed while still keeping the graph fully traversable for both Alice and Bob. To understand this better, let's look at an example. In the first example, we have a graph with n equals 4 nodes and the edges are given as 3, 1, 2, 3, 2, 3, 1, 1, 3, 1, 2, 4, 2, 3, 4. The output here is 2. To explain, the graph initially has 4 nodes and 5 edges. Alice and Bob can both use the shared edges 3, 1, 2, and 3, 2, 3. These edges connect the nodes so that both users can traverse part of the graph. Next, Alice uses her specific edges 1, 2, 4, and 1, 1, 3 to ensure that all nodes are reachable from any starting node. Meanwhile, Bob uses his exclusive edge 2, 3, 4 to fully connect the graph for his traversal. With this setup, all nodes are fully traversable for both Alice and Bob. Out of the 5 edges, only 3 are necessary to achieve this, meaning that 2 edges can be removed. In another example, where n equals 4 and the edges are 3, 1, 2, 3, 2, 3, 1, 1, 4, 2, 1, 4, the output is 0. Here, all 4 edges are required to keep the graph fully traversable for both users, so no edges can be removed. In a third example, consider a graph with n equals 4 nodes and edges given as 3, 2, 3, 1, 1, 2, 2, 3, 4. The output here is -1. This result indicates that it is impossible to connect all nodes such that both Alice and Bob can traverse the graph. For instance, while the shared edge 3, 2, 3 allows both users to connect nodes 2 and 3, there is no way to connect node 1 to nodes 3 or 4 for both Alice and Bob. As full traversal for both users cannot be achieved, the function returns -1 as specified in the problem requirements. Now, let's review the constraints and edge cases. The number of nodes n is constrained between 1 and 10⁻5, and the number of edges is between 1 and the minimum of 10⁻5 and 3 *n. Each edge is represented by a triplet, type U, V, where type is between 1 and 3, and U and V are distinct nodes such that 1 equals U less than V equals n. All tuples, type U, V, are unique. Some edge cases to consider include small graphs with n equals 1 or n equals 2, disconnected graphs where full traversal is impossible, and scenarios with many shared edges where prioritizing their usage may minimize edge removal. Additionally, the solution must handle large inputs efficiently, such as when n is at its maximum value of 10⁻5 and the number of edges reaches 3 *n. To solve this problem, we first considered a brute force approach, which involves exhaustively checking the graph's connectivity for both Alice and Bob after systematically removing edges. The intuition here is straightforward: start with the full graph, remove edges in various combinations, and verify if the graph remains fully traversable for both users. This would allow us to count the maximum number of edges that can be removed without breaking connectivity. However, the challenge with this approach lies in its inefficiency. Simulating graph traversal repeatedly for each edge removal is computationally expensive, especially for larger graphs. With a time complexity of V plus E, this method quickly becomes impractical as the number of edges and nodes increases, making it unsuitable for the given problem constraints where edges can go up to 10 to the power of 4. This inefficiency led us to explore more optimized solutions. A more efficient solution leverages the union-find data structure, also known as disjoint set union. This approach capitalizes on the ability of union-find to efficiently determine connectivity while minimizing redundant operations. The key insight here is to prioritize type 3 edges, as they can be used by both Alice and Bob, which helps optimize the graph's shared connectivity. The process begins by sorting the edges based on their type, ensuring type 3 edges are addressed first. We then use two separate union-find structures, one for Alice's graph and another for Bob's. Type 3 edges are added to both structures, contributing to the connectivity of both graphs simultaneously. After that, the algorithm processes type 1 edges for Alice and type 2 edges for Bob, updating their respective graphs. By counting the edges added to the union-find structures and subtracting this from the total number of edges, we determine the maximum removable edges. Finally, the algorithm checks whether both graphs are fully connected, ensuring all nodes are part of a single connected component. The time complexity of this approach is O(E*alpha v, where alpha is the inverse Ackermann function, which grows extremely slowly. This makes union-find highly efficient and well-suited for the problem's constraints. The union-find approach was chosen because it aligns perfectly with the problem's requirements. Its ability to efficiently merge and check graph components makes it ideal for connectivity problems like this. Prioritizing type 3 edges ensures that shared connectivity between Alice and Bob is maximized, reducing redundancy and making the solution more effective. Additionally, by verifying the connectivity of both graphs at the end, we ensure the correctness of the solution. Compared to the brute force approach, which is computationally infeasible for large graphs, union-find provides a significant improvement in efficiency. While greedy methods might appear to be alternatives, they lack the structured guarantees that union-find offers, making them less reliable. This balance of efficiency, correctness, and scalability is why union-find stands out as the optimal strategy for this problem. One of the key observations that shaped this approach was recognizing the dual-purpose nature of type 3 edges. These edges play a critical role in maximizing shared connectivity, and prioritizing them simplifies the problem significantly. The efficiency of union-find, with its near-constant time operations, ensures that the algorithm can handle the problem's constraints with ease, even for large graphs. Ultimately, this approach achieves the perfect balance between correctness and efficiency. By leveraging type 3 edges and maintaining separate union-find structures for Alice and Bob, we are able to maximize the number of removable edges while ensuring the graph remains fully traversable for both users. This highlights why the union-find method is not just an optimal solution, but also an elegant one for this problem. To start, this problem revolves around ensuring that a graph remains fully traversable for two users, Alice and Bob, while maximizing the number of edges we can remove. The challenge lies in preserving connectivity for both users despite edge removal. A brute force approach provides a baseline solution. The intuition here is to systematically explore all possible combinations of edges, removing them one by one and testing whether Alice and Bob can still traverse the graph. This guarantees correctness, but it is computationally expensive. First, we parse the input, which includes nodes and edges, and classify each edge into three types: shared edges usable by both Alice and Bob, Alice-specific edges, and Bob-specific edges. Representing the graph as an edge list simplifies the process of iterating through edges during the algorithm. Once the input is parsed, the next step is to sort the edges by type. Shared edges are prioritized because they contribute to the connectivity of both users, making them more critical. Separate lists are maintained for Alice-specific and Bob-specific edges. After sorting, we perform a connectivity check using a union-find data structure, also known as disjoint set union or DSU. This structure allows us to efficiently track connected components in the graph. It uses two main operations: find, which locates the root of a node, and union, which merges two components. With DSU initialized, we then test full connectivity. This involves setting up two separate DSU instances, one for Alice and one for Bob. Shared edges are added to both DSUs, while Alice-specific edges are added only to Alice's DSU and Bob-specific edges only to Bob's. By the end, we verify that both DSUs represent a single connected component spanning all nodes. The next part of the algorithm involves simulating edge removal. We iterate through the edges and, for each edge, attempt to remove it. After removing an edge, we rerun the connectivity check for both Alice and Bob. If connectivity is preserved for both users, the edge is marked as removable. The goal here is to identify as many removable edges as possible without compromising the graph's full traversability. Once all edges have been tested, we compile the results by counting the number of edges that can be removed. The final output is the maximum number of removable edges while ensuring that both Alice and Bob can still fully traverse the graph. Now let's discuss some key insights. The use of union find is central to the algorithm's efficiency. Its operations, find and union, run in nearly constant time, specifically O, alpha, n, where alpha, n, is the inverse Ackermann function, making it highly suitable for large graphs. Another insight is the prioritization of shared edges. These edges are critical because they contribute to the connectivity of both Alice and Bob simultaneously, so removing them must be done with caution. And finally, while the brute force approach guarantees correctness, its complexity of O(2 to the power of m), where m is the number of edges, is infeasible for larger graphs. Optimizations, like sorting edges and focusing on shared edges first, help reduce the computational burden. To implement the algorithm efficiently, several data structures are used. First, an edge list is employed to store all edges along with their types: shared, Alice-specific, or Bob-specific. This structure simplifies sorting and iteration over the edges. Next, the union find data structure is used to track connected components dynamically as edges are added or removed. Its efficiency is critical for ensuring the algorithm performs well on larger inputs. Finally, a Boolean array is used to track which edges have been removed, allowing us to avoid redundant checks during the simulation of edge removal. Several key operations drive the algorithm. Sorting the edges is an essential step, as it reduces the number of combinations to test by focusing on critical edges first. Union find operations, like find and union, are used extensively to enable fast connectivity checks. This reduces the need for more expensive graph traversal methods. Additionally, the simulation of edge removal ensures the algorithm's correctness by validating connectivity after each removal attempt. These operations, when combined, form the backbone of the solution, balancing correctness and efficiency. Finally, let's look at some optimizations to improve the algorithm further. A greedy approach to edge removal prioritizes non-critical edges, those that don't contribute to spanning all nodes, allowing us to maximize the number of edges removed. Lazy connectivity checks are another optimization, where we only verify connectivity when removing an edge potentially affects a critical component. Additionally, pruning the search space by stopping early when connectivity is lost helps save computation. In terms of complexity, the worst-case time complexity is O(2 to the power of m asterisk n), where m is the number of edges and n is the number of nodes. However, with optimizations like greedy removal and DSU, this can be reduced to O(m log n). Space complexity is O(n plus m), accounting for DSU and edge storage, making the algorithm practical for real-world use cases. Here, we begin by defining the max number edges to remove function, which will determine the maximum number of edges we can remove while keeping the graph fully traversable for both Alice and Bob. Inside this function, we use a helper function called find to implement the find operation of the union find data structure. This function performs path compression, which ensures that each node in the graph points directly to its root, optimizing future lookups. Next, we define the union function, which merges two disjoint sets. The union function relies on the find operation to locate the roots of the sets being merged and uses the rank array to ensure that the tree remains balanced by attaching the smaller tree under the larger one. After defining these utility functions, we initialize the parent and rank arrays for both Alice and Bob, representing their individual graphs. These arrays are critical for tracking the connected components as we process the edges. We then sort the edges in descending order of type, ensuring that type 3 edges, which are shared by both Alice and Bob, are handled first. Finally, we initialize the removed counter to track the number of edges we discard, and Alice_edges to count the edges included in Alice's graph. We now initialize Bob_edges to track the edges included in Bob's graph. We iterate through the sorted edges, examining their type and endpoints. For type 3 edges, which are shared by both Alice and Bob, we first check if the endpoints are already connected in Alice's graph. If not, we use the union function to connect them in both Alice's and Bob's graphs, incrementing both Alice_edges and Bob_edges. Otherwise, the edge is redundant and can be safely removed, so we increment the removed counter. For type 1 edges, which are exclusive to Alice, we check if the endpoints are already connected in Alice's graph. If not, we connect them and increment Alice_edges. Similarly, for type 2 edges, which are exclusive to Bob, we perform the same check and update for Bob's graph using Bob_edges. Finally, after processing all edges, we check if both Alice's and Bob's graphs are fully connected by verifying if their respective edge counts are equal to n1, the number of edges required to form a spanning tree. If both graphs are fully connected, we return the count of removed edges. Otherwise, it means the graph cannot be made fully traversable, so we return -1. Here, we begin the implementation by importing the necessary packages and defining our solution class. The method maxNumberEdges to remove takes the number of nodes n and the list of edges as input. First, we initialize two separate parent and rank arrays for Alice and Bob, which will help us manage their respective disjoint sets. The parent arrays are initialized such that each node is its own parent. This ensures that we start with every node in its own set. Next, we sort the edges by their type in descending order. This is important because type 3 edges, which can be used by both Alice and Bob, have the highest priority. We then declare variables to track the number of removed edges, as well as the edges used by Alice and Bob. The loop iterates through each edge, and for type 3 edges, we attempt to merge the nodes for both Alice and Bob using the union function. If at least one merge is successful, the respective counters are increment for Alice and Bob. If neither Alice nor Bob can merge the nodes for a type 3 edge, it means the edge is redundant and can be removed, so we increment the removed edges counter. For type 1 edges, which are exclusive to Alice, we check if merging the nodes is possible. If so, we increment the Alice edges counter. If not, the edge is redundant and is therefore removed. Similarly, for type 2 edges, which are exclusive to Bob, we attempt to merge the nodes. If successful, we increment the Bob edges counter, and if not, the edge is counted as removed. After processing all edges, we verify whether both Alice and Bob can traverse their respective graphs completely. This is true if the number of edges used by Alice and Bob equals n1, the minimum number of edges needed to form a spanning tree. If this condition is satisfied, we return the count of removed edges. Otherwise, we return -1 to indicate that it's not possible to make the graph fully traversable for both users. In the find method, we implement path compression to optimize the disjoint set. When finding the root of a node, we recursively set the parent of each node in the path to its root, reducing the depth of the tree and speeding up future operations. The union method combines two sets by their roots. First, we find the roots of the nodes to be merged. If they are already in the same set, the union is not performed, and we return false. Otherwise, we merge the sets by rank to keep the tree as flat as possible. The root with the higher rank becomes the parent, and if the ranks are equal, we arbitrarily choose one root and increment its rank. This ensures that the structure remains efficient for future operations. The method returns true to indicate a successful merge. Together, these helper methods enable the union find algorithm to manage the connected components of the graph efficiently. To solve this problem, we begin with a graph that has 4 nodes and 6 edges as shown in the example. The first step is to sort the edges by type in descending order. This means we prioritize type 3 edges, which can be used by both Alice and Bob, followed by type 2 edges for Bob, and type 1 edges for Alice. After sorting, the edges are organized as 3 2 3, 3 1 3, 2 3 4, 2 1 4, 1 1 2, 1 2 4. Next, we initialize the variables for tracking the disjoint sets and their ranks for both Alice and Bob. The parent_A and parent_B arrays represent the disjoint sets for Alice and Bob respectively, starting with each node as its own parent. The rank_A and rank_B arrays help with union by rank operations. We also initialize counters for the number of edges removed and the edges used in Alice's and Bob's graphs. With this setup complete, we begin processing the edges. The first edge, 3 2 3, is a type 3 edge connecting nodes 2 and 3. We check whether Alice and Bob can connect these nodes by using the find function. Since the nodes are not yet connected, we perform a union operation for both Alice and Bob. For Alice, the parent array updates to 0, 1, 2, 2, 4, and the rank array updates to 0, 0, 1, 0, 0. For Bob, the updates are identical. Both Alice's and Bob's edge counts increase to 1. Next, we process the second edge, 3, 1, 3, which is also a type 3 edge connecting nodes 1 and 3. Using the find function, we determine that these nodes are not yet connected in either graph, so we perform a union operation. For Alice, the parent array becomes 0, 1, 1, 2, 4, and the rank array updates to 0, 1, 1, 0, 0. Similarly, for Bob, the parent array becomes 0, 1, 1, 2, 4, and the rank array mirrors Alice's. Both Alice and Bob now have two edges in their respective graphs. Moving to the edge, 2, 3, 4, which is a type 2 edge for Bob only, we check whether nodes 3 and 4 are connected. Since they are not, we perform a union operation for Bob. The parent array updates to 0, 1, 1, 2, 2, and the rank array updates to 0, 1, 1, 0, 1. Bob's edge count increases to 3. Then, we process edge 2, 1, 4, another type 2 edge for Bob. Nodes 1 and 4 are not yet connected, so we perform another union operation. The parent array for Bob becomes 0, 1, 1, 1, 2, while the rank array remains unchanged. Bob's edge count increases to 4. For edge 1, 1, 2, which is a type 1 edge for Alice, we check nodes 1 and 2. Since they are not connected, we perform a union operation. The parent array for Alice updates to 0, 1, 1, 1, 4, and the rank array becomes 0, 1, 2, 0, 0. Alice's edge count increases to 3. Finally, for edge 1, 2, 4, another type 1 edge for Alice, we see that nodes 2 and 4 are already connected, so we remove this edge and increment the removed edge count to 1. At this point, we verify the connectivity of the graph for both Alice and Bob. For Alice, her graph has 3 edges, which is equal to n1, meaning her graph is fully traversable. Similarly, Bob's graph also has 3 edges, satisfying the same condition. Since both graphs are fully traversable, the solution for this example is the number of edges removed, which is 1. Now, let's look at another example where n equals 4, and the edges are given as 3, 1, 2, 3, 2, 3, 1, 1, 4, 2, 3, 4. As before, we start by sorting the edges by type in descending order. This results in the sorted edges 3, 1, 2, 3, 2, 3, 2, 3, 4, 1, 1, 4. We initialize the same variables as earlier, the parent underscore A and parent underscore B arrays for the disjoint sets, the rank underscore A and rank underscore B arrays for the ranks, and the counters for removed edges, Alice's edges, and Bob's edges, all starting at 0. The first edge, 3, 1, 2, is type 3, meaning both Alice and Bob can use it. By performing union operations for both graphs, we update the parent arrays to 0, 1, 1, 3, 4, and both Alice's and Bob's edge counts increase to 1. Next, we process edge 3, 2, 3, another type 3 edge connecting nodes 2 and 3. For both Alice and Bob, we perform union operations, updating the parent arrays to 0, 1, 1, 1, 4. Both Alice's and Bob's edge counts increase to 2. The edge 2, 3, 4 is type 2, meaning it is only for Bob. By performing a union operation for Bob, we update his parent array to 0, 1, 1, 1, 1, and his edge count increases to 3. Lastly, we process edge 1, 1, 4, a type 1 edge for Alice. A union operation updates her parent array to 0, 1, 1, 1, 1, and her edge count increases to 3. At this stage, we verify the connectivity of both graphs. Alice has 3 edges, which is n1, making her graph fully traversable. Bob also has 3 edges, meeting the same condition. Since no edges needed to be removed, the output for this example is 0. In this problem, we utilize the union find data structure, also known as disjoint set union or DSU, to achieve an efficient solution. Let's break down the time complexity step by step. First, we need to sort the edges based on their type, which is done in descending order. Sorting the edges array takes E asterisk log E time, where E represents the number of edges. Next comes the processing of edges. Each edge is processed exactly once in the for loop, and for each edge, we perform find and union operations. The find operation, which determines the root of a node, employs path compression, reducing the amortized time complexity to O, alpha, n, where alpha, n, is the inverse Ackermann function. This function grows so slowly that it's nearly constant for most practical inputs. Similarly, union by rank, which merges two sets, also has an amortized time complexity of O, alpha, n. Since we process all edges exactly once, the total time complexity for this step is O, e asterisk alpha, n. After processing all edges, we perform a final check to ensure that both Alice and Bob have fully connected graphs. This involves verifying the number of edges in their respective spanning trees, which can be done in constant time, or O1. Now, combining these steps, the sorting phase contributes O, e asterisk log, e, the edge processing phase adds O, e asterisk alpha, n, and the final check is O1. Therefore, the overall time complexity of the solution is O, e asterisk log, e, plus e asterisk alpha, n. Since alpha, n, is effectively constant for all practical purposes, the dominant term here is O, e asterisk log, e. This provides us with an efficient solution to handle large graphs within a reasonable timeframe. Now, let's analyze the space complexity of the solution. The primary contributors are the DSU data structures and the input storage. First, the edges list requires O, e, space to store all the edges. Then, the DSU data structures include arrays for the parents and ranks of nodes. Specifically, the parent underscore A and parent underscore B arrays each use O, n, space, where n is the number of nodes. Similarly, the rank underscore A and rank underscore B arrays each require O, n, space. Together, the total space used by the DSU data structures is O, 2 asterisk n, which simplifies to O, n. Additionally, we use a few scalar variables, like removed, Alice underscore edges, and Bob underscore edges, which take up constant space, or O1. When we combine these components, the input storage contributes O, e, the DSU arrays contribute O, n, and the scalar variables contribute O1. When we summarize the space complexity, the overall space used by the solution is O, e plus n. To put this in perspective, let's compare it to a brute force approach. A naive method would involve generating all possible subsets of edges and checking whether each subset results in a fully traversable graph for both Alice and Bob. This would require generating 2 to the power of e subsets, and for each subset, verifying connectivity using BFS or DFS, which takes O, e plus n, time. The total time complexity of this brute force approach would be O, 2 to the power of e asterisk, e plus n, which is computationally infeasible for large graphs. In contrast, our optimized solution leverages the DSU data structure to efficiently manage connectivity checks, reducing the time complexity to O, e asterisk log, e, plus e asterisk alpha, n. This dramatic reduction ensures the solution scales well even for large inputs, making it orders of magnitude faster than the brute force alternative. Finally, let's discuss the best, average, and worst cases for the algorithm. In the best case, all edges are immediately valid, meaning they already belong to the minimum spanning tree. Even in this scenario, the algorithm processes all edges and performs O, e, find and union operations, leading to a time complexity of O, e asterisk log, e. The average case is similar to the worst case, as all edges generally need to be processed. In the worst case, all edges are processed, and most require union operations, resulting in the same complexity of O, e asterisk log, e. To justify this mathematically, the sorting step dominates the overall time complexity, contributing O, e asterisk log, e, while the DSU operations, with their amortized cost of O, e asterisk alpha, n, are negligible for practical input sizes. As a result, the overall time complexity is governed by O, e asterisk log, e, which provides a highly efficient solution for this problem. One common mistake when solving this problem is failing to carefully distinguish between the different types of edges. In graph problems where edge types matter, such as here where specific edges are designated for Alice, Bob, or both, not accounting for each edge's purpose can lead to incorrect connectivity checks. For example, you might assume the graph is connected for one user when it's actually not, causing your solution to violate the problem's requirements. Another issue is overlooking edge redundancy. Some edges may not be critical for maintaining connectivity, so removing them unnecessarily adds computational overhead. This inefficiency becomes significant for larger graphs, where minimizing redundant operations is crucial. Finally, incorrect handling of disjoint sets in union find operations is a frequent pitfall. If you skip optimizations like path compression or union by rank, your solution may end up being far slower than necessary, potentially degrading to quadratic time complexity. Worse, it might even give incorrect results if connected component counts are mismanaged. Another critical mistake is failing to optimize for shared edges, which are those usable by both Alice and Bob. These edges are pivotal for maximizing the number of removable edges, as they contribute to connectivity for both users simultaneously. If you ignore these edges initially, you risk arriving at a suboptimal solution, retaining edges that could have been removed without consequence. Additionally, it's essential to validate full connectivity after removing edges. This means ensuring that both Alice's and Bob's graphs remain fully connected, as failing to do so violates the problem's constraints. If you skip this validation step, your solution might produce an answer that doesn't actually meet the requirements, even if the code appears to run correctly. When preparing for interviews or tackling similar graph problems, it's vital to have a solid understanding of union find. Specifically, mastering path compression and union birank is crucial, as these optimizations allow you to solve graph connectivity problems more efficiently. Another key insight is to prioritize shared resources. In scenarios where resources, like edges, can be shared between entities, handling these shared elements first often simplifies the problem and streamlines your solution. Alongside this, a strong grasp of graph traversal basics is essential. Being comfortable with BFS and DFS for connectivity checks can be especially helpful in cases where union find is not the most suitable approach. Lastly, always consider time complexity. For large inputs, union find, with its efficient O(m*log n) performance, is often the best choice. Avoid brute force approaches, as their exponential complexity can quickly become infeasible. To deepen your understanding, it's helpful to explore related problems. For instance, LeetCode 323, Number of Connected Components in an Undirected Graph, focuses on identifying connected components in a graph, which is a foundational concept for this problem. LeetCode 684, Redundant Connection, deals with finding and removing unnecessary edges to maintain connectivity. Another related problem is LeetCode 721, Accounts Merge, which applies graph traversal or union find to solve grouping problems. Finally, LeetCode 1584, Min Cost to Connect All Points, emphasizes optimizing connectivity through minimum spanning trees. As for alternative approaches, one option is brute force, where you remove edges one by one and repeatedly check connectivity. While simple to implement, this method becomes computationally expensive, especially for large graphs. A more efficient approach is the greedy algorithm with union find. By prioritizing shared edges first and then processing individual edges for Alice and Bob, this method achieves excellent scalability and is well suited for large inputs, provided you're comfortable with union find. Another alternative approach is to use DFS or BFS for connectivity checks instead of union find. These traversal methods are more intuitive for smaller graphs and can be easier to implement if you're less familiar with union find. However, they're generally less efficient for frequent connectivity checks, particularly in larger graphs. While DFS and BFS work well in certain scenarios, their performance may lag behind union find in terms of scalability. Therefore, they're best suited for problems where the graph size is small or the number of connectivity checks is limited. Thank you for joining me in solving this problem. We explored how to keep a graph fully traversable by removing redundant edges, leveraging union find for optimization. Remember, mastering graph algorithms is essential for competitive programming and technical interviews. Don't forget to like and subscribe for more content like this. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!